Next into the tank, two friends who believe they have a better version of a decadent treat.
Oh, by the way, I made a small change to our pitch.
What kind of change?
Nothing major. Just follow my lead and we'll be fine. Hi, Sharks. My name is Noah King.
And I'm Pete Littig.
We're from the Math Club, and we're here today seeking $100 million in exchange for...
Dude, $100 million?
Can you excuse us for a moment, Sharks?
Nothing major? What are you doing, Noah? We agreed to ask for $100,000, and that was for 50% of the company.
I know, but trust me, Pete, this is $1 billion idea, so we gotta aim high.
I hope you know what you're doing. Wait, did you say $1 billion?
Sorry about that, Sharks. As I was saying, we're seeking $100 million in exchange for a 10% equity stake in our...
Oh, my goodness.
A 10% equity stake in our company, Conic. In our company, Conic. Conic.
Oh, right. How many times has this happened to you, Sharks? It's after dinner, and your sweet tooth is nagging you for some rich, delicious ice cream in a crispy, crunchy cone. But who wants all those calories? And cutting an ice cream cone into smaller pieces is an exercise in futility.
Well, luckily for you, now there's Conic. Ice cream in a cone cut into bite-sized slices. Circles and ellipses of your favorite flavors with a ring of mouth-watering waffle cone all around the edge.
But that's not all. You also get scrumptious, tasty parabolas and hyperbolas when we miss with the knife and slice the cone wrong.
So, Sharks, who wants to make their money go in supersonic directions with our sweet Conic sections?
Your valuation's astronomically high. I'm out.
Oh, we're sorry to hear that, Lori. Mr. Wonderful?
I'm choking on the valuation. I'm having a real hard time with it. I can't go there. I'm out.
Barbara? Robert?
I'm out, Robert. And I suggest you go out, too.
Let me tell you, you guys are great. I mean, it's a really, really fun vibe you have about you. I love the humor. I love you guys, but I can't do it. I'm out.
Both of you? Damon, please. You like ice cream, don't you?
I'm actually upset, you know why? Because I like it.
But you really came in with a big valuation. I'm out.
Well, that's everyone. No deal for us.
I can't believe you wouldn't want to get in on the ground floor here. These Conic are the dessert of the future.
Come on, Noah. Let's go.
You're going to regret not buying a piece of this company when we're swimming in piles of cash and there's a delicious ice-cold parabola in every mouth across the country.
We wish you nothing but success.
Good luck.
Good luck.
Can you believe that, Pete?
Actually, I think I can. You asked them for $100 million. And how many have we sold so far?
Sold? We haven't even made any yet. Like you said, cutting up ice cream cones is really hard.
Well, why don't we get some ice cream to cheer ourselves up? And while we're at it, we can practice making your little conies.
Okay.
Hey, Noah, did I ever tell you the story about one day when I was in high school and I stayed home sick and ended up doing a bunch of math?
No, I don't think you ever told me that story.
Well, my mom is a retired high school teacher, but back when I was in high school, not her high school, but back then she was still actively teaching. And on this particular day that I stayed home sick, I think I was a sophomore. I had just finished watching like all the morning cartoons and all the morning game shows, and like The Price is Right was over. And it was like, what am I going to do now? So sitting in the living room, I saw a stack of my mom's math textbooks, and I just decided to start rifling through them.
You mean you didn't go from Price is Right straight into Jerry Springer?
I did not, sadly. No, I made the better choice and educated my mind. Well, the book that I ended up picking up and really spending a lot of time with had a chapter in it on the geometry of conic sections. And so I spent probably 2 or 3 hours on my sick day solving problems from this textbook related to conic sections. I was completely fascinated.
Wow, Pete, you really knew how to take advantage of a day off back then, didn't you? Yep. So forgive me for asking what may be a pretty obvious question, but what are conic sections?
No forgiveness needed. I don't think that's an obvious question. I think it's something some people just haven't encountered. So I'll tell you what, rather than giving you a definition, let's do something different instead. How about I show you what they are?
Sure. All right. I'm all eyes.
All right. Do you have a flashlight?
Yeah, I have a flashlight in my closet here. Give me a second just to find it. Okay, I've got a flashlight now, and I think I might have some idea of where you're going with this, but why is it that you wanted me to get a flashlight?
Okay. So are you in an environment right now where it's dark enough for you to shine the flashlight on a wall and look at the light patterns that are formed?
Yeah, I absolutely am.
Cool. And I just got out my handy dandy trusty mag light, and I will do the same thing where I am.
Oh, Pete, mine is not a mag light. Mine is a Coleman. Is this going to work?
No, we have to cancel the show.
Darn it.
Sorry, Mash. Of course it's going to work. But let me ask you this. Is your flashlight circular?
Yeah, it's just a regular standard flashlight with that circular piece of protective glass at one end where the light comes out.
Perfect. All right. So that's an important part of what we're about to do. And actually, for our listeners at home, if you all have circular flashlights handy and you want to follow along with us, that would be totally cool.
All right, Pete. So what is it you want us to do?
Well, first, turn your flashlight on, and I want you to point it directly at the wall and tell me what shape you see when you've got it perfectly straight on.
Well, I'm seeing a circle of light on the wall because there's a circular opening that the light is coming out of, and it's going straight at the wall.
Right, exactly. Now, if you start to tilt the flashlight one direction or the other, not too far, but just play around with it, you should see some changes happening to the light, and I'm curious if you can describe them for us.
Okay, so what I'm doing now is originally I had the flashlight held so that it was perpendicular to the wall, but now what I'm doing is I'm taking the back end of the flashlight and I'm tipping it down a bit so it's no longer parallel to the floor, and the circle is kind of elongating. It's turning into like an oval.
Yes, it is. And that oval shape that you're seeing actually is a very precise shape that you have encountered probably many times in your life. You've certainly seen it many times, and you might even have studied it, say, in high school. The word, however, isn't oval. It's a different word. Do you happen to know what it is that I'm thinking of?
I think you're talking about an ellipse.
It is called an ellipse. And the way you have created it is by simply tilting your flashlight a little bit, you have caused the light pattern to elongate from a circle into an ellipse. And the first question I have for you is, why is it doing that?
Well, I think what's going on here is as the light is coming out of the flashlight, I think it's kind of coming out in a cone shape. And when I'm holding it perpendicular to the wall, the end of that cone that's touching the wall is a circle. But as I tip the flashlight so that it's no longer exactly perpendicular to the wall, that's elongating the part of the cone that's hitting the wall. Kind of like when you go to the theater and you see a spotlight coming down from up high and it's illuminating the actors, but it's not shining straight down on the stage. It's shining at an angle. So what you get on the ground on the stage isn't a perfect circle, but kind of an elongated circle.
Yeah, that's a great example. It is an ellipse that you see down there on the stage. And what I like about that example in a theater is that oftentimes those stage lights are so bright, you can see the beam of light coming down from its source as it illuminates the actor and the stage beneath her. So that's great. That's the cone that I want us to focus on for a moment. In fact, that's the cone that gives us the name conic section. Conic meaning of a cone. Oh, okay. That makes sense. And you're exactly right about how when that cone is slanted relative to the wall, that there is a spreading out and elongation effect. And now the light pattern that is created is elliptical. It actually forms an ellipse. So let's take one step in the abstract direction and enter a world of pure geometry. We'll go back to the flashlights in a moment. So if I take a cone, a mathematical cone, which in your mind, at least for now, you can picture simply as an ice cream cone. So it's got a point and it is circular shaped as it extends from the point, we'll call the vertex, and it extends down to the circular opening. That's an example of something called a right circular cone.
That there cone is right circular.
It is. Now, if you take a plane, which you can imagine as a flat piece of paper, or mathematically speaking, an infinitely thin, infinite flat surface, and you pass that plane through the surface of the cone itself, keeping it perpendicular to the axis of the cone, and look at the intersection that's created, you'll see a circle. And if you slant the plane in one direction or another, you will see the intersection change shape from a circle to an ellipse.
Okay, so if I understand you correctly, the geometric cone that you're describing abstractly is being represented in our example here by the cone of light coming out of the flashlight.
Exactly, that's right.
And the geometric plane that you're describing in your abstract example is being represented here by the wall.
Yeah, it is. And here, the wall is fixed, and you're moving the cone around by moving the flashlight. Usually in the pure geometric setting, we think of the cone as staying fixed, and we move the plane around. But essentially, you have described exactly the analogy that I have in mind.
Okay, and to make sure that listeners can visualize what we're talking about here, we're going to include a link in our show notes to an image that we put together showing these different conic sections, both using the flashlight and in a more abstract model like Pete's describing. But Pete, there's something that I just can't help but wonder as I look at this. It seems to me like there might be a difference here that's not being properly reflected in the example with the flashlight and the wall, because when I picture what you're describing abstractly, the intersection between the cone and the plane is just an infinitely thin edge around the circle or the ellipse. But when I shine the light on the wall, I'm seeing a completely filled in circle of light or a completely filled in ellipse of light on my wall. That entire thing is not really the circle or the ellipse. It's just the outside border, right?
Yeah. And you know what? That's a really good question to think about in general. So a circle is not a solid disk with a circular boundary. A circle is simply that infinitely thin curve. You could think of it as a bent piece of wire that makes the shape of a circle. It's like a ring that you could pass your arm through. It is not solid. And you're right, the light shape on the wall is solid. So what we're really talking about here is the boundary between the light shape and the darkened wall. It's really just the outside of that light shape that we're using as a representation of the conic section.
Got it. But here's another question, Pete, because I'm sitting here playing with this flashlight and tipping it up and tipping it back, and I'm going from circle to ellipse, back to circle, then to an ellipse. And when I was doing that, I just rotated the flashlight a little too far, and now the entire light cone is not hitting the wall anymore. Some of it's hitting the wall, but some of it is now off of that plane and hitting the ceiling. And so I don't really have a circle or an ellipse anymore, and I'm not sure how to describe what's going on here.
It sounds like you've created a kind of interrupted ellipse. So if your ceiling were higher, I think you'd probably still see an ellipse on your wall, but instead the ceiling is getting in the way. Of course, if you turn the flashlight at a very steep angle, for example, if most of your interrupted ellipse is on the ceiling and not the wall, then I think you'd have a new conic section. The ceiling would still be getting in the way, but it wouldn't be an interrupted ellipse anymore.
So you're saying it would be some sort of interrupted conic section, just not an ellipse. Okay, so what would that new conic section be?
Well, let me describe it this way. A couple of months ago, I was looking at the table lamp on my nightstand. And when I looked at the light pattern it was making on the wall, I realized, oh, that's a hyperbola. There's a curve right at the boundary of the light and the shadow made by the lampshade. And that curve happens to be a hyperbola. It's a conic section. And in fact, it's the new conic section I mentioned just a minute ago. You could make one right now if you held your flashlight straight up and down and moved it close to the wall.
I see what you mean. I'm doing that exactly now. I have the flashlight aiming straight up at the ceiling and laterally right up against the wall, and it is making sort of a boomerang-shaped curve on the wall.
Yeah, exactly. So you are creating a new conic section called a hyperbola. And this hyperbola, this curve, unlike the circle and the ellipse, does not close round on itself to make a closed shape. It extends infinitely far. And of course, mathematically, there's no reason not to talk about infinite planes. It would extend infinitely far up,
meaning that if I didn't have a ceiling here and I had a powerful enough light source, I would see that hyperbola going up and up and up and up. I would never see an end to it.
Exactly. And here's something super interesting about that hyperbola. As the left and right parts of this hyperbolic curve extend further and further up into infinity, they are getting slightly farther apart from each other. However, they are asymptotically approaching a pair of lines that you can't see, but that are there. And so that's a very interesting phenomenon here that is definitely not present in the circle or the ellipse, nor is it present in the one remaining conic section that we haven't yet talked about.
And what's that one?
Well, this is a difficult one to actually see with your flashlight because it appears and then disappears almost instantaneously as you're moving your flashlight around on the wall, but it's called a parabola. I'm sure that's a familiar term.
Oh, yeah, I've definitely heard of a parabola before, and I remember graphing them back in algebra in high school.
Yeah, you certainly would have. And in fact, if you're looking now at either the light cast by your flashlight with it pointing vertically upwards, or if you're looking at a table lamp at the side of your bed, you might look at the curve that's formed on the wall and think, oh, that must be a parabola, right? It kind of sags down and turns around and goes back up. Well, it certainly looks like it could be a parabola because it has that general shape. But in this case, these are actually hyperbolas. To create a parabola, you would need to hold the flashlight at a very particular angle. And that angle is equal to the angle that the light cone itself makes as it comes out of your flashlight.
So how do I know where that angle is if I'm just aiming a flashlight at the wall? I suppose it's pretty hard. Maybe if I had some kind of smoke or mist in the room that illuminated the cone, it would be a little easier to do this. But without it, it seems like that would be pretty hard.
Yeah, so I'm going to describe to you what's happening with my flashlight. So I'm holding it perpendicular to the wall, so I've got a circle. Now I'm going to take the tail end of the flashlight and start to pull it downward so the light is rotating up. So now I've got an ellipse, and as I keep going, ellipse, 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 parabola, hyperbola, 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 only at that exact angle, and I don't actually know when it occurs. So I think what we need is a different way to see how parabolas show up in the world. Fortunately, there are many, many ways, and probably the most familiar can be found at a drinking fountain. So the next time you're at a drinking fountain, push the button, watch the water coming out of the fountain, and look at the shape that the water forms as it emerges from the nozzle and then heads back down to the basin of the fountain. That water stream is forming the shape of a parabola.
Oh, okay. So still a curve, like a hyperbola, but a very specific curve.
Yeah, a very specific curve. And here's another way to see it. take a ball, toss it up into the air, and watch the path that that ball follows as it goes up, turns around, and comes back down to Earth. That's another example of a parabola.
I see. So a parabola is basically that arc shape, kind of like if you look at a hanging telephone line between two poles or the cable on a suspension bridge, right?
Well, let's think about your telephone wire example. So you're saying, oh, this is like a parabola. It's just instead of going up and coming back down, it starts off by going down and then turning around to go back up. There's your parabola, right?
Right.
Actually, no. It's not a parabola, but you made a very good guess, and you're in good company because Galileo also thought it was a parabola, and it's not.
Oh, man. I hope this doesn't mean I'm going to get excommunicated by the Pope.
Oh, I've already excommunicated you several times, my friend.
Okay, so the sagging telephone wire is not a parabola. This must be what you were talking about earlier when you said a lot of people can confuse parabolas and hyperbolas. So this is actually a hyperbola.
Actually, it's not a hyperbola either. It's a totally different curve. Although it looks a lot like both of the curves that we just named, it is significantly more complicated to figure out what it is, but it's a curve called a catenary.
A catenary? Is that like a cross between a cat and a canary?
I thought I saw a pussy cat.
I think you've got it. So actually, the catenary curve was the subject of some very interesting historical mathematical challenges that were being issued back and forth by mathematicians in the late 17th century. And many famous mathematicians were involved in the hunt for the actual equation that defined the catenary curve. And I believe it was first discovered by one of the Bernoulli brothers, who had challenged his older brother to figure it out, but he got it first. And his older brother got stuck because, like Galileo, he kept thinking, this must be a parabola. I just need to figure out how to see it mathematically.
Okay, so this catenary curve, which isn't a parabola or a hyperbola, is it another type of conic section?
It's not. In fact, the curves that we're looking at here, these conic sections, can all be described algebraically, which is why you might have encountered them in an algebra class. They all have equations that look like x squared over 4 plus y squared over 9 is equal to 1. So basically polynomial combinations of x's and y's where the power involved is never greater than 2. The catenary curve, however, is a so-called transcendental function, and it's much more difficult to nail down. In fact, think of it this way. We talked in our last episode about Newton's law of cooling, and the cooling equation itself was exponential. That's another example of a transcendental curve, and it's not immediately obvious how to get your hands on the formula for a transcendental curve. So the catenary belongs to a different class of functions, and it's a little more remote, a little less accessible than the conic sections.
Okay, so if I'm understanding correctly, then there would be no way to take our plane and intersect it through a cone and get the result of the catenary curve. That's not a result we could get. But the other shapes we talked about, the circle, the ellipse, the hyperbola, the parabola, all of those can be created by taking a slice or a section of a cone, which I guess is why they're called conic sections, right?
Yeah, exactly. Now, let me say one interesting thing about the cones that we're talking about, because in fact, the model that mathematicians use for cones is not just like a single ice cream cone. It's like two ice cream cones that have been glued together vertex to vertex. And so each of these cones would extend infinitely far, one downward and the other upward, in a shape that might be called a double cone. Can you picture that?
Yeah, let me make sure I'm picturing it right. I'm picturing, like, for example, a lighthouse that has a light shining out from both sides. And so it's making a cone maybe going out to the right and another cone going out to the left, and they're meeting, their vertices are meeting in the center right where the light is. Am I picturing the right thing?
You are, yeah. And so the reason that we have two cones together, and by the way, each of the individual ice cream cones in this larger double cone has a special name. It's called a nap.
Yeah, Mr. King, do you think you can get one across the plate, or do you need to take a nap?
And it's spelled differently from the sleepy nap. It's spelled N-A-P-P-E. So we've got this giant double cone. Now you may say, well, Pete, why do we have a double cone? Because when I intersect the plane to get a circle, it only passes through one of the naps, say the lower one. Same with an ellipse. So why do we even need the upper nap? Do you have a guess, Noah?
I do, but I'm having a hard time formulating it. But here's what I'm picturing. When I take a plane and intersect a cone to make a circle, it's just going to go through one of the naps. When I rotate that plane a little bit and make an ellipse, it's still only going to go through one of the naps. And when I rotate it even more and get into that area of the parabola, it's still only going to intersect one of the naps. But when I turn it even further and make that hyperbola, it seems to me like it's going to go through both naps. And I think this has something to do with what I remember about graphing hyperbolas in algebra when I was back in school, because I remember that there wasn't just one curve to the hyperbola. There were two sort of opposite curves. Good memory. That's exactly it. It's that hyperbolas have two branches. That's what we call them. So the light image on your wall that, say, your table lamp is making is only showing you one branch of the hyperbola. There is actually another branch that lives in the other nap. And so hyperbolas have two disjoint components, these two curves that turn away from each other, extending out to infinity. And the parabola also has this feature of extending to infinity, but it only lives in one of the naps because the plane has been rotated, and I liked the way you described that, to the furthest point it can go without piercing the second nap. And that's why it's so tricky to nail down that parabola with the flashlight. It only happens when the plane is exactly parallel to the lateral surface of one of the naps. As soon as you rotate it a little bit more, boom, it hits the upper nap and creates a hyperbola. I getcha. That's interesting. So are these four conic sections that we've discussed so far the only four types of conic sections that there are?
Well, that's an interesting question because there's one very interesting point now on this double cone that we haven't talked about and that we haven't asked our slicing plane to pass through. Any guess what that special point is?
Well, considering the fact that a cone only really has one point that seems in any way unique, it's got to be that vertex, right? Where the two naps connect to each other.
Yeah, that's it. And I want to give you a little bit of praise for making this observation. You said, well, naturally speaking, there's only one point that could be considered special. That's a super powerful bit of mathematical intuition. And mathematicians look all the time at whatever concept they're considering. They ask, are there special elements here? What is the special element? I want to focus on that because something different is going to happen at that special element.
Isn't that special?
So what happens if we pass our slicing plane through that vertex of the double cone? What are we going to get?
Well, I guess it kind of depends on the orientation of the plane, but I can picture a couple of different things that could happen. If you have your cone oriented so that there's an upper nap and a lower nap, so sort of like sitting there like an hourglass, right? Where the wide parts are above and below, and then the narrow part where they come together is in the middle. If I put the plane so that it was slicing through the vertex and it was also parallel to the ground, that intersection would just be one infinitely small point, wouldn't it?
It would just be a point. And in fact, if I move that plane, keeping it horizontal to the floor, and I move it either down or up by the smallest of bits, suddenly that point will explode out into a circle. And as I move the plane up and down and pass it through that vertex point, I will see circles shrinking down to a point and then enlarging and then turning around and getting smaller until they shrink to a point again. And so that point, it's almost like it's trying to be a circle of radius 0, but it's a very degenerate circle.
And then the other way I could picture the plane intersecting that point is if I rotated the plane so that it was perpendicular to the ground instead of parallel to the ground. And I think what you would get in that case would look very much like a hyperbola where the two branches meet right in the center and touch each other at a point.
Yeah. And in fact, what you're describing is a degenerate form of a hyperbola. And what it's going to look like, in fact, what it will be is simply a pair of crossing lines. So the lines will intersect at a single point, and that simulates this notion of trying to take the two curved branches of a hyperbola and trying to force them closer and closer and closer together until the two curved parts meet. Well, the very moment that they meet, suddenly everything becomes a rigid pair of straight lines that intersect at the vertex.
Got it. Now, in both of these examples that I gave you, you used a new term. You said they were degenerate. What does that mean?
That's the word that mathematicians use to indicate that some geometric construct has collapsed and taken on a very different nature. So think about one of the examples we just discussed. The horizontal cross sections of the cone, which are usually circles, collapse down to a single point when the intersecting plane passes through the vertex. And the geometry here really has collapsed. A point doesn't have any of the usual properties that a circle has. It doesn't have a radius. It doesn't have a circumference. It doesn't inscribe an area. All of the familiar structure possessed by a circle, totally gone.
Got it. So I guess what we're saying is that there are 4 regular conic sections and there are 2 degenerate conic sections. Is that right?
It's almost right. So first of all, we usually use the word non-degenerate, although regular somehow makes more sense here, but the word regular gets way overused in mathematics. So we use the term non-degenerate to describe the 4 conic sections that we have been discussing from the beginning: the circle, the ellipse, the parabola, and the hyperbola. And now among the degenerate examples, there's actually one more. There's a third example. And I'm wondering if you can figure it out.
Well, I'm assuming that it also has to go through that central vertex point of the cone. And I'm also assuming that it's not going to be created by placing the plane parallel to the floor or perpendicular to the floor. So it's going to be somewhere in between. I'm picturing now that the plane is passing through the vertex, but it is slightly askew.
Yeah. And in fact, it is a very particular orientation that we need to strike. And that orientation is related to the special orientation required to create the parabola.
Okay. Well, I'm assuming then that the plane has to be oriented in such a way that it just barely touches the edges of the cone itself.
Yeah. What do you think it's going to create? What's that intersection going to look like?
Well, I'm picturing that as we take that plane and we rotate it, we're going to rotate it just enough so that the upper nap of the cone and the lower nap of the cone just barely touch the plane. So I think it's going to look like a ray shooting out from the vertex and traveling along the very edge of the upper nap. And then there'll be another ray shooting out in the opposite direction from the vertex and traveling along the edge of the lower nap, right?
Yeah, you're picturing it right, but I think there's a simpler way to describe it. So you're thinking of 2 rays that start from the same point, namely the vertex of the cone, and then head in opposite directions. So,
oh, I get it. They're going to form a line, aren't they?
Now you've got it. And that line is a kind of degenerate case that is similar to both the parabola and the hyperbola, but it's different from the crossing lines that we talked about earlier.
Okay, then just to slightly amend what I said a few minutes ago and to try and sum up what I think you just explained, there are 4 types of non-degenerate conic sections: the circle, the ellipse, the parabola, and the hyperbola, as well as 3 types of degenerate conic sections, which are a point, a pair of crossed lines, and a line.
Yeah, you've got it now. And what's interesting is we can't actually create those degenerate forms using our flashlight. Our flashlight is only going to allow us to create the non-degenerate conic sections. And as we noted, The parabola is particularly difficult to nail down.
But I loved how when we were talking about the parabola, you were able to nail it down by giving us some real world examples of where a parabola shows up in the physical world, like the arc that we see in the stream of water that's coming out of a drinking fountain or a hose, or the curve that a ball takes when you throw it up in the air and it comes back down. But what about these other conic sections? Do they also tend to show up in the real physical world somehow?
Interestingly, the answer is yes. And in fact, also in very familiar ways, although maybe not as viscerally obvious. So, for example, the planet that we are all living on is in orbit around the sun. Well, the path that a planet orbiting a star takes is elliptical. So the Earth is orbiting the sun and it is following an ellipse. Now, the ellipse is not particularly elongated. It's very close to being circular, but it is in fact not a circle. And this was a major discovery in astronomy that, as you alluded to earlier with Galileo, was fraught with political ramifications. But it is in fact the case. The Earth is orbiting the sun along an elliptical path. So that's a very familiar, if difficult to feel, phenomenon.
That's pretty cool. And speaking of orbits, if memory serves, sometimes when a comet passes close enough to the sun, not close enough to get snagged by its gravity well and pulled into an orbit, but just enough to be affected by the sun and curved a bit, doesn't that curve define some sort of a conic section as well?
Yeah, a comet that enters and is not snagged by the sun's gravity well will slingshot around the sun on a hyperbolic path and then eventually leave our solar system, not ever to come back again.
Man, Pete, I can't help but notice how cool it is that we started this conversation with just a simple flashlight shining on the wall, and we've come all the way to the paths that planets and comets follow as they're hurtling through space. And the abstract mathematical concept that links it all together is these conic sections.
It's super beautiful. And the conic sections have been known since antiquity. The Greeks studied them at length. Although the Greeks didn't know about these kind of planetary relationships, nor did they understand, as far as I know, that objects thrown into the air here on the surface of Earth would follow a parabolic arc. But the fundamental mathematical construct, which is very simple, even in its algebraic form, it's polynomials of degree 2, that very simple model can explain so much about the world that we live in. It's really amazing.
Oh, I could not agree with you more. I think this is all super cool how it all relates together. Now, before we wrap up, Math Club, we have a little announcement to make about the next couple of months.
That's right. My family and I are going to be out of town, and so I will be away from the Math Club for about a month and a half. So Noah has come up with a couple of ideas about what to do while I'm away.
That's right. These plans are still a little bit tentative, but if all goes according to plan, we will still be bringing you new episodes throughout the summer. We just won't have Pete. I am working to line up a series of guest hosts and guests that I'll be able to talk with and bring you episodes throughout the summer until Pete gets back.
And my only ask of you, Noah, you can have whoever you would like on the show, but please, not Alexa.
Oh, no way. Never again. We've been burned by her before, and she is not getting near the mic.
Oh, come on, you guys. I'm totally better now.
Yeah, we know you were very helpful during the anniversary show, but I just don't think we're going to let you co-host again. Anyway, Pete, do you want to tell listeners how they can reach out if they have a question or a comment or they want to suggest future episode topics?
Listeners, if you would like to reach out to us, please do so on our SpeakPipe page. The address is speakpipe.com/mathclubpodcast. Or why not send us a tweet? Our handle on Twitter is @mathclubpodcast. And as always, you can send us an email. Our address is mathclubpodcast@gmail.com.
All right. Thanks for another great episode, Pete. I think I'm going to go back and finish my ice cream now before it's completely melted.
Oh, it was a great episode. In fact, I would say it was pretty iconic, wouldn't you?
I guess I would.
Bye, Math Club. Bye, Bad Club.